In this video, we're going to work on creating time-speed charts for objects in freefall. So our problem says a student drops a ball from the top of a building. The ball remains in the air for 3 seconds. Neglect drag. Alright, so let's start off by making a time-speed chart as it asks us to do. I know that time always starts at 0, and in this case, at the start of the problem, the ball is in the student's hand, and so the speed also starts at 0. Now, during the duration of the problem, after it leaves the hand to as the ball falls down, the ball is in free fall, which means our acceleration is 10 meters per second squared. Now your class might be using 9.81 meters per second squared, but especially on these time speed charts, these problems have extra tolerance, so if you want to use 10 meters per second squared, you can. So that means after 1 second, the ball's speed would have increased to 10 meters per second. 2 seconds, 20 meters per second, and 3 seconds, 30 meters per second. So the problem asks us with what speed did the ball strike the ground. I know I was stopping at 3 seconds, and so 30 meters per second would be the final speed. In our next problem, a student launches a cannonball upwards with an initial speed of 30 meters per second. Neglect drag and the initial height of the cannonball. Alright, so we're going to start our time speed chart again. But this time, the start of the problem is when the ball leaves the cannon. So right here is our initial time, and our speed is 30 meters per second upward. Now, this ball is in free fall as well, so it's in mid-air, it's aerodynamic, and there's no other forces acting on the ball besides gravity, so I know that the acceleration, once again, will be 10 meters per second squared. Now, after 1 second, so inside the barrel of the cannon, the ball's speed increases rapidly. However, once the ball leaves the cannon, then gravity takes over, and our speed will start to decrease. So here the ball is rising, but with a decreasing speed. So after 1 second, the speed is 20 meters per second. After 2 seconds, the speed will be 10 meters per second. After 3 seconds, the speed will be 0. So what's happening right there is the ball has stopped. So just for a second, the ball comes to a stop, and that happens at the highest point right here. So this is at 3 seconds, the ball comes to a stop. Now I'm actually only halfway done with my problem. So at 4 seconds, the ball is going to start to come back down. And as the ball comes back down, the speed increases. Now I use speed, so I'm not going to put a negative sign on anything. If you're using velocity, you could use a sign convention and call these ones negative. But I'm going to say as the ball comes back down, the speed is increasing by 10 meters per second every second. So the question then is when to stop. Well, in this problem it says we have flat ground right here. It also says to neglect the initial height of the cannonball. So what that tells me is I need to keep going until my initial speed is equal to my final speed. Basically, with no air resistance, this ball is going to come back down with the same speed as it left the cannon. So I'm going to answer these in opposite order. It says how long will the cannonball remain in the air? That's looking for this time right here, which is going to be 6 seconds. Now it says what was the cannonball speed and what direction was the cannonball traveling after 4 seconds? Remember, after means at. So at 4 seconds, we were traveling 10 meters per second. And it says what direction? Well, 4 seconds would be after the ball stopped. So at 4 seconds, the cannonball has to be maybe somewhere like right here for 4 seconds, which means in my problem, the cannonball is on its way back down. So anything before 3 seconds where the ball stopped, the cannonball was on the way up. Anything after 4 seconds, the cannonball was on the way back down.